To Math 136. We'll be meeting on Monday, Wednesday, Thursday, and Friday between 1 and 1:50. This is a class about calculus. The first question we want to ask, what is calculus and what we study in calculus? One answer is, in calculus we study functions. This is a simplification in many ways because calculus is a huge part of mathematics. One could write an essay what calculus is all about, but essentially if I have to use just one word, what calculus is all about, what we study in calculus we study functions. In the same way, in calculus we study functions, and in the same way as in geometry we study shapes, for example triangles, circles, and so on and so forth. In arithmetics we study numbers, 1, 2, 3, 4. So in calculus, and again that's a simplification in many ways, but in calculus we study functions. Now there are two basic operations one can do on functions. Given a function, I can compute the derivative of that function, or I can compute an antiderivative of the given function. Essentially this is calculus 1. Essentially, that's what we study in calculus 1. In calculus 1, we study the concept of derivative of a given function. Now, this is calculus 2, and what we'll be doing in this class, we'll be studying the concept of antiderivative. In a way, something opposite to derivative of a given function. From calc 1, we know that derivative can be used to find the equation of the tangent line to the graph of a given function at a specific point, the slope. Now, antiderivative can be used to compute the area under the given function from some point, let's say from A up to B. So what is an antiderivative and how we define an antiderivative of a given function? Let's say we have a given function. I'll take this function cosine, for example. Take this function cosine x. Let's say this is the given function. Well, given a function, I can compute the two operations. One, I can compute the derivative of that function. And from calc 1, we know that the derivative of this function cosine is the function negative sine x. So given a function, in this example cosine, the derivative of this function is the function negative sine x. Now, what do we mean by an antiderivative of this function cosine? Well, an antiderivative of this function cosine is going to be a function with the property that if I take this function and compute its derivative, that will give me exactly the function that was initially given, the function cosine x. So we know that this function sine has this property, because if I take this function sine x, then this is an antiderivative of this function cosine, because the derivative of this function sine is cosine. But this is not the only one antiderivative, because if I consider this function sine x, let's say plus some constant, sine x, let's say plus 1, this is also an antiderivative of this function cosine, because the derivative of this function sine is cosine, and the derivative of 1, the derivative of constant, that's 0. So the derivative of the whole function sine x plus 1 is exactly equal to cosine x. So sine x plus 1 is an antiderivative of cosine. Of course, if I take another constant, sine x plus 2, or for example sine x, consider now this function sine x plus 2 or plus 3, or in fact if I take any constant c, any number c, it could be positive, negative, or 0, then this function sine x plus c is also, this function sine x plus c, this is also an antiderivative of this function cosine, because the derivative of sine is cosine and the derivative of any constant is 0. So the derivative of the whole function sine x plus c is exactly this function cosine x. So just to repeat, if I have this given function cosine x, we mentioned that given a function, the two operations one can do on function. One is you can compute derivative of this function, and derivative of this specific function, derivative of cosine is negative sine. But also I can go on the other side and compute the antiderivative of that function. And any antiderivative of this function, cosine x, would be this function sine x plus c, where c is any constant, positive, negative, or 0. So in general, if I have a given function f, then again, there are two operations I can do. One is I can compute f prime. This is derivative of this function f. Given a function f, I can compute its derivative. And this is essentially calculus 1. We know how to compute derivative of a given function, but an antiderivative of this function f, what we mean by an antiderivative of this function f is any function, I'll use the same letter but big F, is any differentiable function f with the property that if you compute derivative of this function f prime, that will give you exactly the function that was initially given to us. So f prime derivative of f is the given function f. That's what we mean by an antiderivative of a given function. So I have another example. Well, again, that was the function that we just considered, the function cosine x. And one antiderivative of this function cosine is the function sine x. This is the graph of this function sine x. This is the graph of this function sine x. This is one antiderivative, this function right here, sine x, this is one antiderivative of this function cosine. But if I consider this function sine x plus 1, this is the function sine x plus 1, this is also an antiderivative of this function cosine, and the reason is derivative of sine x plus 1 is cosine. And here's another example. This function is the function, this is the function sine x plus 2, sine x plus 2, and so on and so forth. If we take any constant c, then this function sine x plus c, this is going to be an antiderivative of this function cosine. So let's consider another example. As a function, let's now take this function 3x squared. So we know that there are the two basic operations I can do in function. One is I can compute derivative of this function from calculus 1. We know that derivative of this function 3x squared is 6x. That's the derivative of this function. And now this new concept of antiderivative, well, what's going to be an antiderivative of this function 3x squared? Well, that's any differentiable function with this property that if you compute its derivative, that will give you 3x squared. So we know that derivative of this function x cubed is exactly 3x squared. That's the power rule. So this function right here, this is an antiderivative of this function 3x squared. But of course it's not unique because I can add 1 to this function, and this new function x cubed plus 1, this is also an antiderivative of this function 3x squared, because derivative of this function is exactly 3x squared. And in fact, if I take any constant c and consider this function x cubed plus c, this is going to be an antiderivative of this function 3x squared. And the reason is that derivative of this function x cubed is 3x squared, and derivative of any constant c, that's 0. So derivative of the whole function x cubed plus 3, x cubed plus c, this is 3x squared. So here is again this function that we just considered 3x squared. That was the function that we just considered. We know that 6x, that's the derivative of this function 3x squared. And here, this function indicated in the first function, this is the function x cubed. This is the function x cubed. And this is one antiderivative of this function 3x squared, because derivative of x cubed is exactly 3x squared. This is another example of antiderivative. This function right here, this is the function x cubed plus 1. And this is also an antiderivative of this function 3x squared because the derivative of this function is exactly 3x squared. And here is another antiderivative. This function, that's the function x cubed plus 2, x cubed plus 2. And this is another antiderivative of this function 3x squared because the derivative of this function x cubed plus 2 is exactly 3x squared. So in general, if we take any constant c, then this function x cubed plus c, that's going to be an antiderivative of this function 3x squared. So really what this constant c is responsible for in this formula is this constant c would be essentially shifting this function up and down. So if c is positive, you shift this function x cubed c units up. And if the c is negative, then you lower this function. So now let's make a connection between this concept of derivative and antiderivative, just looking at this simple example. So again, this function 3x squared, this is the graph of this function 3x squared. We know that the derivative of this function 3x squared is 6x. That's the graph of this function 6x. And this is one antiderivative. That's the function x cubed plus c, where c is any constant. This is the antiderivative that corresponds to c equals 0. This is the antiderivative that corresponds to c equals 1. That's the antiderivative that corresponds to c equal 2. And this is the antiderivative that corresponds to c equal 3. So we'll be using this notation that the collection of all those antiderivatives, i.e. the functions of this kind x cubed plus c, where c is any constant, we call this collection indefinite integral, and we use the symbol indefinite integral of this given function 3x squared. So here's another example, a little bit more general, because now let's say that n is any number and consider this function x to the n. So from calculus 1, we know that the derivative of this function using the power rule, the derivative of this function would be n times x to the n minus 1. That's the derivative of this function. So going to the right hand side, computing derivative, we know this is essentially calculus 1. Now this is new, this is calculus 2. So an antiderivative of this function, that's going to be any differentiable function with this property that its derivative is exactly the function x to the n. So using the power rule, we can check that if you compute the derivative of this function, that will give you exactly x to the n, and so this is an antiderivative of this function x to the n. And again, like in the previous example, I can add 1 to this function. That really means that you will be shifting this function 1 unit up. This is also an antiderivative of this function x to the n. And in fact, for any constant c, you can take any constant c and consider this function plus c, and this is an antiderivative. In a way, that's the most general antiderivative of this function x to the n. And again, we'll be using this notation, integral of this function x to the n. That was the given function x to the n dx. That's just a symbol. That's just a part of a notation that we'll be using. The symbol dx by itself doesn't mean anything. It's just a part of the notation. So the indefinite integral of this function x to the n is exactly this function x to the n plus 1, x to the n plus 1, n plus 1, all divided by n plus 1. This is just one antiderivative of this function x to the n, but in fact we can take this function and shift it up or down. For the shifting, that's the constant c. This is the constant c that is responsible for the shifting. And let's assume that n is not equal to 1 from obvious reason, because if n is equal to -1, then the formula doesn't work because we have 0 in the denominator, which is not a valid expression. So this formula holds as long as n is not -1. And we'll be assuming for simplicity that the x's are positive. And how do we check that this is indeed an antiderivative of this function? Well, when we take this function and we compute its derivative, then that will give me exactly this function x to the n. So now I want to make a connection between this concept of derivative of one hand side and antiderivative. And again, we'll look at this example. Let's say that the function of interest is the function 3x squared. Call this function f. So f of x, this is the function 3x squared. That's the graph of this function 3x squared. And let's say that we have some given point x0 or x0 in the domain of this function, and we want to write an equation of the tangent line. This is the tangent line. This is the straight line, the tangent line to the graph of this function at this specific point. So to compute to find the equation of the tangent line, we use derivative. For equation of the tangent line, we use derivative because all we know is we need to compute the slope of this line, which is exactly, this is the information that we get from the derivative. So we know that if this is my function f, 3x squared, then f prime, the derivative of this function, is 6x. So now let's use the point slope formula for this tangent line. The point slope formula says y minus y0 is m times x minus x0. So m, that's exactly the slope, and y0, that's this point, and x0, that's exactly this given point. So now, as we just mentioned, m is f prime of x0. So this was my function f. First I need to compute f prime of x0, which is going to be 6 times x0. So f of x0, this is the function 3x0 squared, and that's equal to f prime of x0, which is 6x0 times x minus x0. So for example, if we take this point x0 to be 1, so if we take this point x0 to be 1, for example, then, well, we have y minus 3 times 1, which is y minus 3, and that's equal to 6 times 1, which is 6 x minus 1. So if we simplify that, then we get that y equals 6x minus 3. This is exactly this straight line, which is the tangent. This is the tangent line to the graph of this function at this specific point when x0 is equal to 1. When x0 is equal to 1, this straight line, this is the line y equals 6x minus 3. 6x minus 3. So again, to compute to find an equation of the tangent line to the graph of a function at a specific point, I have to use the concept of derivative. Derivative tells me what is the slope of this tangent line. Now let's consider the same function but different question. So function still is the same. The function is 3x squared. But let's say now we want to compute the area. We have some number a and b given, and I want to compute this blue area. This is the area underneath the function f between this line x equals a and x equals b. So to compute this area, for that we use an antiderivative. But which of those antiderivative? We can take any antiderivative that we want to. For example, I can take this one. So this is, let me call this antiderivative big F. So f of x, this is going to be equal this function x cubed. this is going to be equal to this function x cubed. This is indeed an antiderivative of this function 3x squared. The reason for this is very simple, because if I compute derivative of this function big F, if I compute derivative of this function big F, so f prime of x, this is exactly 3x squared. So this is indeed an antiderivative of this function 3x squared. So how do we compute this area indicated here by this blue color? All I have to do is I have to take one antiderivative of this function f. So here's my function f, small f. And I have to take one antiderivative, any of those. For simplicity, I'll take the one with constant c equals 0. But we could equally well take any other. And then this area, let me call this A. This is the area of interest. Then this area A, this is going to be simply use this antiderivative. Take this antiderivative and apply this antiderivative f first at this point B, so f of B, and then minus, take the same antiderivative and apply this antiderivative now at this point A, so f of A. So this is equal, well, f of B, this is the function f of B, this is going to be b cubed, this is going to be b cubed minus f of A, this is going to be a cubed. So for example, if A is equal to 1, if this point right here, if this point is 1, and this point right here, this point B, if this point B is 2, well, then this area A, this is equal to b squared, which is 2, this is 2 cubed, because this is b cubed. So this is 2 cubed minus, this is a cubed, which is 1 cubed. So that's 7. So that's the area, 7 units squared, whatever the units might be, but that's the area of the function, that's the area underneath the function f between the straight line x equals a and x equals b, and the area is bounded above by this function f and below is bounded by the x-axis. That's the green, that's the blue area, 7 units squared. So just to repeat, in calculus that's a simplification in many ways, but in calculus we study functions, and given a function f, I can compute derivative of this function f prime, or I can find an antiderivative of this function f. This is essentially calculus 1, this is essentially calc 1, and this is essentially calculus 2. So this is what we'll be studying in this semester. So in calc 2, we'll use this concept of antiderivative to find the area underneath the given function, because if we call this function small f, for example, then to compute this area, all I have to do is I have to find this big function f. Any function f with this property that its derivative is going to be the given function f. And once I have this, then this area is going to be simply, let me call this point A and this point B. Then this is the big function f applied to this point B minus the big function f applied to this point A.